Good afternoon, councillors. We're just here to basically give you a bit of a verbal rundown, and after we finish a chance for our questions, into the report that's sitting there in front of you right now, onto the Newcanto Tri-County Council's road of Kildonna Road, which is, as well know, the access between Windawindi and the Ashbarty Inland Port. It's important to state when you see this road that it is only the road between the roundabout at the highway intersection and the start of the entry to the inland port. It doesn't include the side roads and various other sections of the roads that we're talking about that we want to upgrade. It's only this section. This is the only section we have funding for to be able to do. It's a section that we will be talking about today, and indeed it's the section that the report that we've got actually has mentioned. And here we see the actual turn off onto Kildonna Road from the New Highway roundabout. The road itself, the geometry is okay, being that the turns meet standards, the runoffs and the elevation above the road is all quite good, but the road surface itself has degraded. And here is the actual inland port itself. Whilst the river traffic has taken a lot of traffic off the road from the point of view of holistic Australia-wide, it has sort of seen local increase in traffic and a lot of, as we say, damage because of increased use. This slide just shows a couple of the issues we're seeing on the road, and we're seeing extensive potholing, we're seeing shoving, and we've had quite a few complaints from the road users within the Shire about the quality of the road and about how the repairs are not necessarily keeping up with what the community's expectations of that road are. And as a result, Council conducted a quite an extensive survey using several contractors to come through and basically perform some substantial measurements upon the road. With the completion of those surveys, we can then use known industry standards, being the Australian Guides to Pavement Technology, Pavement Evaluation and Treatment Design, and the TMR Pavement Rehabilitation Manual, to then devise ways and means of interpreting the data to give us the best result for a longer term design. The first survey we completed was the easiest one to do, was roughness, and you can see the survey here. These are taking changes from the start of the roundabout to the Ashbarty terminal, and you can see that the international, the IRI, the Roughness Index of Kildonna Road, it actually exceeds the performance expectation. The performance expectation is 1.9. In this case, we've actually the performance expectation, well, so the reality is we're well above that. This indicates that the road is indeed in need of an investigation or further looking at to determine why it is behaving in that manner. Here is the TMR guidelines, basically what roughness we should intervene and look at that. And you can see we've basically passed that too, so we're ready to look at something here. One of the other tests that the contractors completed was rutting. It was done using that machine on the technology on the picture on the left, being the VW rutting meter. Rutting in itself, we all know what it is, but that's probably the best way to look at it is the picture on the left there. You see that straight, you see that slight dividend, that slight dent. The issue with this is that it basically allows water to pool up on the road, and as we all know, water is not the friend of the engineer. And it then presents a hazard to vehicles using it. Anything that pulls in there then creates a problem as far as trafficability goes. We've had the rutting survey completed, and this is the result. As you can see, overall the rutting is not particularly bad. It is, however, we do have a couple of sections where the rutting has exceeded the maximum, or the recommended maximum, and we've got a couple of sections where it's approaching, it. So this does indicate that there are sections of the road that's seeing degradation through rutting, possibly pointing to failure in the base. The next survey that we completed upon Kilgonnan Road was a falling weight deflectometer. Now this technology uses a 40 kilonewton load to basically measure the rebound of the road as the survey vehicle drives along the road and completes the survey. As you can see, this is actually taken in situ by the ARRB, so sort of showing the Kilgonnan Road being measured. And yeah, it is a very effective tool. It's non-destructive in that you don't have to dig up the pavement to get a reasonably good understanding of what's actually going on under the pavement and under the base and under the pavement. And this is the results that we have received from the falling weight deflectometer. What it's allowed us to do is to break that road down into changes, being start points and finish points, and link them into like sections, sections that basically behave the same way in an engineering way along the road. And in this case here, we found 5 sections. We'll just refer to the section A, B, C, and D, and we'll run through those individually later on. The advantage of what we're seeing here is we now have an expectation of what is going on in the base and in the subgrade of the road. And this is an example of the sort of information we can glean from the falling weight deflectometer surveys, where we can basically use the measurements of the deflections, the sort of the rebound and penetrations, to give us an estimate of the California bearing ratio, which is a pretty universal strength parameter that's used to determine the modulus of the stiffness of the soil underneath the road, to then allow us to design cover. There's a couple of ways of doing this, and it's always a key parameter we need to have, and the advantage of that falling weight deflectometer, we now have this as part of the start of this work, so we can now use this to form an estimate of what's going required to complete the roadworks. By using those empirical methods, we've basically now been able to describe the sections, and we've basically come up with moduli for the actual layers that are important to us. So, you know, the granular layers have industry-defined parameters. They're manufactured fill, and the asphaltic concrete, the AC, what we'll see in the engineer's report, have engineered parameters that our modelling and our data use. However, the soils and the subgrades, they don't. They can be individual because they are still an in situ native material. Thus, we've now been able to quantify what those materials look like, and this allows us to start looking at repairs. With regards to the running surfaces, we are in a warmer traffic zone, so Austroads and industry bodies basically give us a guide as to what we can use for the seal on the surface. So if we want to go with a spray seal, Austroads basically indicates that, you know, as it's a rural highway with, you know, with no high stress, with a average truck use of 2,000 vehicles, it's going to recommend a HS2 double seal, which is a standard seal for sort of works. You know, 2 layers of seal, 2 layers of sealant, being the bituminous material, and 2 layers of the pebbles in it to provide that sort of seal and protector over that base. The AC, the asphalt bearing course, however, we're basically going to look at your binders, and we're going to use a more durable binder to handle the heats that we get out here in Cato Can Shire Council. Okay, road key. In the past, we could use older empirical methods for designing roads, and this is just a couple of examples using it. The traffic data, so the amount of roads, the amount of road usage is a key parameter. That's that design traffic that is measured in equivalent standard axles. What we do is we, as road designers, break down the traffic into loadings, and we basically design for the loadings, and allows us to come up with reasonably robust designs. The other parameter we need to know is the strengths of, or the modulus of the materials in the base and under the base, and probably the picture on the left explains that best. You can see the green arrow, the California bearing ratio, which is that strength estimate that we gathered from the deflectometer data, estimates the California bearing rate of the subgrade is 5%. The traffic that we've calculated for that road is indicated in the blue, and we can then use that to basically indicate what the road will require. These are very broad brush and very loose measurements, but there's a lot of empirical data to say this sort of base model stuff can work, and for a lot of very rural councils this is a really great tool for designing overlays and roads. The picture on the right is specifically granular overlay thickness. So if you're going to overlay a road, you can basically, by knowing the traffic and by knowing the characteristic deflections which we determine from those that falling weight deflectometer data, you can then basically determine an overlay, and you can basically see that by following the green arrows up, which represents the design traffic we've killed on the road, where that intersects with the characteristic overlays of those sections, you'll then be able to take across and say you'll be able to define a granular overlay. It is worth stating here, and as the geometries I've killed on the road do not allow us to do much in the way of overlay except for section E at the end of it. Unfortunately, the roadside infrastructure is such that we can't just apply an overlay. That was then. These days, however, we now use a industry package called Surface 7, and indeed all our remediations were done with using Surface, and this has the advantage that it can actually do a lot of the thinking and the smartiness aspect can be done, the optimization can be done using Surface. And here we can see we've loaded up the traffic data into and the traffic, the way the traffic spreads, so the axle loadings, the type of axles we're seeing, that's a single axle, single tyre down the bottom of the picture rather, single axle double tyres, quad axle double tyres. This really designs an engineering work for this road. We then start by loading up the parameters into our layers of the road. So you're seeing down the bottom, you're seeing a granular road base. We've then got some subgrades that we took from the estimates from the falling weight deflectometer survey to then give us, that's what the in-situ road is. We then model the basis of the model, and the Surface has then used itself to describe what's basically popped up, and within an organisation it will say certain iterations don't work, and it will then supply you with thicknesses that can be used to build the road, and it basically provides you a very good remediation answer for any of these roads. So this is how this process was done. It's why each individual section has differing engineering parameters. Once we had parameters, we then basically used our extensive database of how we cost things to basically come up with costing models. So basically costed the primers and the stabilisations and whatever else that are required for all these roads, and we've banged these models into basic cost estimates. And this is the next slide here. This model here shows all of the various models that were estimated. The pink blocks show the expected reseals. The unfortunate, or the downside to thin bituminous ceilings is that they do require resealing to preserve the base and stop the road from degrading to get the maximum out of it. And you can see that there's going to be a couple of sections in a 20-year life of fault interruption, and that is probably going to be one of the criteria that hopefully councillors will make when you make the decision, taking into account when you make the decision, is the reseal time and interruptions. Section A, basically running from the roundabout to intersection 1. It's only 40 metres in length, so it's not a particularly big section. It does, however, and it does have shoulder area associated with it, but it is not insubstantial, and it is that first section. The two optimised costs we've come up with is a spray seal, the less durable option. It has the lowest initial cost of all the options. Total cost is relatively low for this section. Basically comes down to $49 a square metre. However, the more durable option, and probably the one that we would prefer, would be the use of foam bitumen to stabilise the base and get some strength into that base to withstand that loading. And then we put an asphalt running surface. Section B, which is between the Russ Hughes Road and J. Peterson Road. Again, slightly larger than the previous section, slightly different. And here we have the costs, $59 a square metre for the spray seal with a little bit of fill to make up the base. So we excavate out and put some fill, or $129 for a full depth AC pavement. Okay, section C, another shorter section. Very similar to the previous one, $59 a square metre for the spray seal option, or $132 a metre for the foam bitumen stabilisation and then AC surface. Slight differences in remediation due to the differences in the ground conditions in each of these sections. Section D, this is a longer section, 900 metres, obviously going to be relatively more expensive than the other section. But you can still see on a unit cost per metre, $60 a square metre is not terribly much for the spray seal base, or $125 for the foam bitumen stabilisation and then laying an AC surface on top of it, which will get a lovely driving result. And section E, in the entrance to the Ash Barty terminal, you're seeing again another 800 metre section, not the longest but quite a large section. Again, $67 a square metre for the spray seal, or $127 for full AC overlay. Now, section E is the only section where we don't have pavement geometry issues with regards to height. So we are able to just purely put an overlay either way onto the existing base to give us the strength into the base and the square course. So there's options for the council to select there whichever way we wish to go with the funding. The recommendations that we're going to see here are, in all cases, the asphalt options will give the best results in terms of product quality, durability and life. They do come at a higher cost, both in the initial outlay and over the overall life, but there's less interruptions. And that's, in a commercial road, it can be argued that some of those interruptions are quite massive, isn't it? The spray seal, massively lower cost. You know, we can basically get a job started for relatively easy and quickly, but it does have a lower ride quality, it's noisier, and there's more interruptions due to the seal and repair that are required. So when we add the two costs up in order for your decision, enabling your decision, we've got the spray seal surface options over the total project. In terms of net present value, the the two options are not that far apart. You're looking at $412 a square metre for the entire project, or $488 in terms of net preservated dust. It's arguable that the higher cost of the AC, of the asphalt, is a better option for council. That's put that to you. And thank you for your time.